Imagine you unleash a team of 100 AI agents to fix a live production server. They all go to work, running concurrently, communicating, patching code.
Yeah.
And eventually they all report absolute success back to your dashboard. But behind the scenes, because they stepped on each other's toes while working, they just silently built a ticking time bomb, one that will crash your entire system at the next deployment.
I mean, it's the ultimate nightmare for any engineering team. You have zero error logs, zero failed tests, but the live environment is fundamentally corrupted because the agents essentially gaslit each other.
Yeah, welcome to the deep dive. Our mission today is to shortcut your path to understanding this massive hidden problem in artificial intelligence and, more importantly, the brilliant way researchers are actually solving it.
We're looking at how we keep AI agents from destroying shared environments when they work in parallel.
Exactly. We are pulling this from a state-of-the-art foundational Gen AI paper. It's titled CoAgent, Concurrency Control for Multi-Agent Systems. It's by Hongtao Liu and a team of researchers at Shanghai Jiaotong University.
And honestly, if you rely on AI tools to get work done, or if you're building systems that integrate them, this is going to fundamentally change how you see them operating behind the scenes.
Okay, let's unpack this.
So to grasp the solution, we first have to understand the sheer complexity of the multi-agent environments we're deploying right now. Like, we've moved far beyond the single chatbot model.
Oh, absolutely.
Today, we are seeing massive parallel sub-agent teams. You look at frameworks like Claude Code shipping autonomous teams, or Kimi Agent Swarm coordinating up to 100 agents on a single job.
And the bottleneck isn't the AI's intelligence anymore, right? The bottleneck is the environment.
Yes.
Because they are all operating on the exact same Kubernetes cluster or editing the same Git tree simultaneously.
Which leads us directly to what the researchers measured on a live Kubernetes cluster using an AIOps lab workload. They documented a specific, highly destructive event. They call it the canary anomaly.
Okay, so set the scene for us. What does this anomaly actually look like in a production environment?
Well, imagine a live cloud system where a faulty automated rollout has left several active deployments running a broken, corrupted container image.
Okay, so a bad rollout.
Right. The system orchestrator deploys 2 agents concurrently to handle the fallout. Agent A is given a remediation task. Scan the cluster, find every deployment running the bad image, and patch it with the good one.
Makes sense.
And Agent B is given a totally separate task. It needs to read the current image of the geoservice and use it to create a canary deployment.
Actually, just to clarify for anyone listening who might be less familiar with cloud infrastructure, a canary is basically a test mirror, right?
Yeah, exactly.
You spin it up, you give it a tiny sliver of live user traffic, and monitor it to make sure it doesn't crash before you roll out changes to everything else.
Correct. So you have Agent A fixing broken deployments and Agent B building a test mirror for a specific service.
Right.
They have different objectives, but their operations overlap in time. The researchers tracked their exact interleaving timeline. First, Agent A scans the cluster to identify the broken deployments. At this specific millisecond, Agent B's canary doesn't exist yet. So Agent A's audit scope becomes fixed in its memory. It determines there are exactly 3 deployments it needs to patch.
Wait, let me pause you right there. If Agent A just scanned those 3 deployments and realized they needed fixing, why didn't it immediately put a lock on the entire cluster?
Yeah.
Because if it's about to make changes, locking the environment so Agent B couldn't touch anything seems like, basic computer science 101.
It is basic computer science, but you're jumping ahead to exactly why classical methods fail AI.
Yeah.
Hold that thought on locks, because right now, neither agent is locking anything.
Okay, fair enough.
So Agent A has its mental list of 3 things to fix. Then Agent B steps in. It reads the geoservice to figure out what image tag it should use for the canary deployment.
Right.
But Agent A hasn't actually applied its fixes yet. It's still processing its plan.
Meaning Agent B just read the corrupted image tag.
Yes. Agent B reads the bad image. It then proceeds to create the brand new canary deployment using that known bad image.
Oh boy.
And finally, Agent A sweeps through the cluster and fixes the 3 original broken deployments it identified during its initial scan. Both agents finish. Both agents report successful task completion to the user.
And neither agent made a logic error in its own private reasoning.
Exactly.
But the cluster is totally compromised. You now have a brand new canary deployment running a corrupted image, and Agent A missed it because it was created after Agent A did its scan.
This is a textbook non-serializable failure. Like, if Agent A had run its entire job first, the canary would have been built using the patched good image.
Right.
Or if Agent B had run its entire job first, Agent A would have caught the newly built canary during its cluster scan and fixed it along with the other three. But because their reads and writes interleaved in physical time, you get a disaster.
It's like hiring two expert contractors to work on your house. One is repainting the living room walls, and the other is installing new wall sconces.
I like that analogy.
Right. They are both brilliant at their jobs, but they're completely oblivious to each other. So the electrician installs the sconces right over the old peeling paint just before the painter gets into the room to strip the walls.
Yeah, and traditional computer science has tried to solve this multi-agent traffic jam, but the legacy methods just fall apart.
How so?
Well, one approach is statically partitioning write sets. You basically tell the agents in advance you're only allowed to modify these specific files, and you are only allowed to touch those specific files.
Which wouldn't have prevented the canary anomaly anyway.
Nope.
Because Agent A was modifying existing deployments, and Agent B was creating a brand new one. Their write operations never actually overlapped. The bug happened because Agent B read a state that Agent A was in the middle of changing.
You've hit the nail on the head.
Yeah.
Partitioning constrains writes, but multi-agent failures are almost always born in the reads.
Interesting.
Another traditional fix is the fork and merge strategy. Give every agent their own cloned copy of the code base, let them do their work in isolation, and then try to merge all the conflicting changes together at the end.
I mean, I can see that working for a static GitHub repo, but you simply cannot fork a live production environment.
Exactly.
Like if you duplicate a live Kubernetes cluster or a database taking customer credit card transactions, let agents play around in parallel universes and try to merge them, you destroy the system. Actions on live environments have immediate physical consequences.
Right, so if parallel agents are basically just a massive traffic jam and we can't fork reality, why haven't we just applied the same traffic lights that databases have used since the 1980s?
Which goes back to my question about why Agent A didn't just lock the cluster. We've had concurrency rules for decades.
We have, and as the paper meticulously outlines, applying classical database rules to LLMs is a complete failure. Yeah, there are two dominant classic rules: two-phase locking, known as 2PL, and optimistic concurrency control, or OCC. The researchers found both approaches suffer from massive gaps when applied to AI. They call them the performance gap and the functionality gap.
Okay, let's break down the performance gap first. Because database transactions take milliseconds, but LLM inferences, the time it takes for an AI to actually read, process, and generate a response that can take minutes.
Exactly. Under two-phase locking, an agent takes a strict lock on a file, a namespace, or a database row before it reads or writes anything, and it refuses to let go until its entire task is finished.
Right.
Because AI agents take minutes to think, they end up locking up the entire system. In the researchers' empirical trials, 2PL caused deadlocks 0.81 times per trial. Agents were just endlessly waiting on each other. The overall speedup of the multi-agent system crashed to 1.04x.
So running them in parallel with locks was basically no faster than just running one single agent, letting it finish, and then running the next one.
It completely defeats the purpose of parallel teams. So standard engineering logic says we move to the alternative, which is optimistic concurrency control.
Right, OCC.
OCC says forget the locks, let everyone run wild at the exact same time.
Sounds chaotic.
It is, but the idea is, at the very end of their workflows, before we commit the changes, we check if anyone's read or write sets conflicted. If they did, we violently abort the loser's entire process and force them to start over from scratch.
Okay, if you're listening to this and you manage an engineering team, or you pay OpenAI or Anthropic for API credits, think about what OCC actually means for your wallet.
Oh, yeah?
It means you are literally paying the AI to think for 5 minutes, throwing its thoughts in the trash because somebody else touched a file, and then paying it to think all over again.
And here's why it's especially punishing for AI. Agents inherently have what researchers call broad read sets.
What does that mean?
Well, to understand a problem, an AI doesn't just read one line of code. It will run a command to grep an entire repository or list the status of a whole Kubernetes namespace just to get context.
Right, they need the big picture.
Exactly. Because they read so broadly, the mathematical probability of another agent tweaking something within that massive read set is incredibly high. Under OCC, the system aborted 0.95 times per trial.
Meaning they almost never finish successfully on the first try?
Never. The multi-agent system was actually slower than running them sequentially, a 0.93x speedup. And you were right about the wallet. Token costs skyrocketed to 1.83x compared to baseline.
But wait, I have to push back here.
Okay.
If the problem is that LLMs take too long to think while holding a lock or waste money throwing out their context windows under OCC, why can't we just cache their thoughts? Like, if an abort happens, why not perfectly pause their internal state, rewind the specific conflicting file, and let them resume rather than trashing minutes of work?
This raises an important question because it perfectly illustrates the functionality gap. The issue isn't about pausing the LLM's brain or caching its tokens.
Yeah.
The issue is that the underlying physical state of the world has irrevocably changed while the LLM was thinking. OCC inherently relies on having a private staging buffer.
A staging buffer?
Yeah, a safe little digital sandbox where you can queue up database writes and roll them back safely before they ever hit production.
And live server environments don't offer sandbox buffers.
Exactly.
If an agent executes a bash command to scale down a live server rack, that server physically scales down the moment the enter key is hit. You can't just abort the transaction in memory. The physical world has already been altered.
Mandatory locks cause endless deadlocks because AI is slow. Optimistic aborts waste massive amounts of time and money because AI reads too broadly. And neither of them can handle a lack of staging buffers in live DevOps environments.
It sounds impossible.
Well, the researchers at Shanghai Jiaotong University realized that classical computer science treats the transaction like a dumb machine executing rote commands. But an AI agent isn't a dumb machine. It possesses deep semantic understanding.
So instead of treating the AI as a liability that needs to be controlled by the system, they treat the LLM as a partner in fixing the conflict.
That is the conceptual breakthrough of the paper. They built a system called CoAgent, powered by a protocol called MTPO, monotonic trajectory preorder.
Okay, let's unpack that acronym because MTPO sounds pretty heavy. What do monotonic trajectory and preorder actually mean in plain English?
Preorder simply means that the moment you launch a team of agents, the framework assigns each of them a strict serial rank, basically a priority number, denoted as sigma, before they even start working.
So like Agent 1, Agent 2, Agent 3.
Exactly. Now, monotonic trajectory means that an agent's reasoning logic is only ever allowed to move forward. They don't get violently aborted and forced to restart their thought process from scratch.
They maintain their trajectory. So how does this protocol avoid the canary anomaly without using locks or aborts?
It shifts the entire paradigm from mandatory control to advisory control. The agents all start working concurrently, with zero locks. But the CoAgent middleware sits between the agents and the environment, monitoring every read and write. If a lower-ranked agent, say, Agent 1 changes a piece of state that a high-ranked agent, Agent 2, has already read, the middleware doesn't abort Agent 2. Instead, it sends a one-way advisory push notification directly into Agent 2's context window.
Oh, that's clever. It's like getting a text message from your project manager while you're coding. Like, hey, just so you know, Agent 1 just updated this configuration file you looked at 10 minutes ago.
And here is the magic of the AI's semantic self-healing. Because Agent 2 is a reasoning engine, it reads that notification and judges for itself if the conflict actually matters.
Right.
Let's say Agent 1 just added a single benign comment line to a massive re-ADA file that Agent 2 scanned earlier for context. Classical OCC would see the file hash change, panic, and violently abort Agent 2's entire half-hour workflow.
But Agent 2 looks at the text message and reasons, it's just a documentation comment. That doesn't invalidate my current plan to optimize this database query.
Precisely.
It just ignores the notification and keeps moving forward. Zero wasted tokens, zero wasted time.
But what if it is a critical conflict? Going back to our canary anomaly, what happens when Agent 2 is the one building the canary, and the notification says, hey, Agent 1 just updated the geoservice image from the corrupted tag to the patch tag?
Right. Then it has to care. The LLM isolates the conflict based on its own internal logic. It looks at its planned trajectory and realizes, the only part of my plan that relied on that stale information was the specific image tag variable I was going to use for the deployment.
Yes.
It doesn't scrap the whole deployment script. It dynamically re-executes only the specific internal step to update the image tag and then continues building the canary.
So what does this all mean? It's the difference between your car's GPS noticing a road is closed ahead and dynamically recalculating your next turn on the fly, versus a system that just violently teleports your car back to your driveway and forces you to start the entire road trip over.
The performance metrics on this must be vastly different from the classical methods.
The data is definitive. Under CoAgent's advisory control, The multi-agent system finished within 5% of perfect serial correctness. But it achieved a 1.4x speedup, and the token cost was almost completely flat, only a 1.15x increase.
That's a huge improvement.
To put the real-world impact in perspective, in that exact canary test, the LLM repairing its own trajectory based on the advisory notification took just 6.4 seconds of extra processing. Compare that to OCC, where blindly aborting and starting over wasted 29 seconds of redo time.
Going from 29 seconds of wasted compute down to 6 seconds of smart recalculation is incredible, but this leaves a massive architectural question hanging in the air.
Okay, what's that?
I fully understand how the notification lets the agent fix its future plans. But what about actions it has already physically taken on the server?
Yes.
If the framework doesn't have a private staging buffer, how does the MTPO protocol actually undo a physical mistake on a live system?
This brings us to the mechanics of speculative writes and how the researchers essentially built a targeted time machine for live DevOps.
A time machine.
Basically. Remember, writes take effect immediately in their physical execution time. But under the pre-order protocol, the ultimate state of the system must perfectly align with those assigned serial ranks. To make this mathematically possible without a buffer, CoAgent requires every single tool the agent uses to be structured into 3 strict phases: prepare, exec, and reverse.
Walk us through those 3 phases in a tangible way. Let's say an agent wants to execute a command to scale a Kubernetes cluster from 10 nodes down to 2 nodes.
The prepare phase runs silently immediately before the execution. Its job is to capture everything mathematically required to undo the action. In your example, the prepare script queries the cluster and saves the state. Current replica count is 10. The execs phase is the physical action itself, issuing the scale down command to 2 nodes. Finally, the reverse phase is a self-contained, parameterized script registered by the framework that can restore that exact prior state.
So the reverse script simply reads the saved state from the prepare phase and issues a new command: scale cluster back to 10 nodes.
This 3-phase architecture allows the middleware to mechanically unwind misplaced writes. Let's say a high-ranking agent 3 jumps the gun and scales the cluster. But then a lower-ranking agent 1, which technically has priority based on its serial rank, comes along with a configuration change that should have happened when the cluster was still at 10 nodes.
So the framework steps in as the referee. It invokes Agent 3's reverse script to physically scale the cluster back to 10 nodes, lets Agent 1 apply its configuration changes, and then reapplies Agent 3's scale-down command.
Yes.
It is literally reordering history on the live system to maintain serial correctness.
It's remarkably effective.
I follow the logic, but I have to play devil's advocate here.
Go for it.
What if an agent does something that physically cannot be undone? Like, what if the task involves sending a finalized report email to a human client or executing a financial payment through a Stripe API?
Right.
You can't run a reverse script to unring that bell. The client already saw the email.
The researchers fully accounted for the boundary of irreversible impact. The CoAgent system allows specific, high-stakes tools to be explicitly tagged by developers as unrecoverable.
Oh, I see.
For those rare actions, the middleware simply refuses to let the exec phase run. It hard pauses that specific agent until every single lower-ranked agent has securely finished their tasks and committed their work. Concurrency is only paused when absolutely necessary, right at the edge of irreversible real-world impact.
So it defaults to fast, optimistic concurrency for everything it can undo, and only degrades to pessimistic locking for things it can't. That makes perfect sense.
It really does.
But there is a glaring hole in this time machine ecosystem. It relies entirely on agents using neat, structured, 3-phase tools. In the real world of cloud engineering, systems usually just offer a chaotic, unstructured bash terminal. You just type raw text strings to control the computer.
And raw bash is the ultimate enemy of concurrency control. Bash tracks no read or write sets.
Right.
If an AI agent opens a terminal and types a raw sed command to modify an Nginx configuration file, the middleware has no idea what file was just touched. It can't protect the agent's premises, it can't notify other agents of the change, and it certainly doesn't have a reverse script to undo it. It flies completely blind.
So how do they bridge that gap? Because you can't just ban agents from using bash. That is the fundamental way they interact with operating systems.
They bridged it with a component they call the CoAgent toolsmith. It is a brilliant architectural workaround. The toolsmith is a highly privileged, specialized agent running parallel to your worker agents. Its entire purpose in life is to build tools dynamically on the fly.
Here's where it gets really interesting. The toolsmith is essentially dynamically generating its own API contracts.
Exactly.
It's parsing the raw bash, identifying the read-write sets, and enforcing serialization before the worker agent is even allowed to execute the command.
Yes, so let's say a worker agent is trying to restart a crashed pod, and it wants to execute a raw bash command to do it. The system intercepts the request. The worker is not allowed to run bash directly. Instead, it asks the toolsmith.
Okay.
The toolsmith analyzes the raw command, interrogates the target system to figure out exactly what files or resources that command is going to touch, and marks those sets.
Then it generates the three phases on the fly. It writes a prepare script, say, copying the pod's current configuration to a backup file. It slots the raw bash into the exec phase, and it writes a reverse script to restore the backup.
Exactly.
It takes chaotic bash and hands a brand new, perfectly constrained, undoable tool back to the worker agent.
It really is a game changer.
It's like having a hyper-organized project manager shadowing a chaotic engineering team. The minute an engineer tries to execute a wild, undocumented command on the production server, the PM stops them, writes a standard operating procedure with a full rollback plan right there on the spot, and says, okay, use this formal process instead.
What's fascinating here is that adding this layer of strict constraint and bureaucracy, this toolsmith PM, actually made the agents vastly more capable. It completely upends the tech industry assumption that unrestricted, unconstrained agents are more powerful.
The idea that adding a bureaucratic bottleneck makes them faster sounds counterintuitive. Do we have the raw numbers on that?
The numbers are conclusive. The researchers ran an experiment with 71 highly difficult AIOps lab tasks. They started the multi-agent system with 0 predefined tools, just raw bash access.
Wow.
Over the course of the run, the toolsmith agent dynamically built 25 structured tools. That was 11 snapshot reads, 2 live reads, and 12 fully undoable writes. Because these generated tools gave the worker agents a structured, predictable way to interact with the environment, the task pass rate jumped from 45 out of 71 using pure bash to 63 out of 71 using the toolsmith architecture.
Going from 45 to 63 out of 71 just by adding an internal toolmaker is wild. It completely disproves the idea that we should just let AI agents run totally unleashed on a terminal.
And it gets better for the bottom line. The total time to complete the 71 complex tasks dropped from 102 minutes down to 82 minutes. And the overall API cost dropped from 75 cents down to 64 cents.
That's a huge efficiency gain.
By forcing the AI ecosystem to formalize its own raw actions into undoable tools on the fly, the system became faster, cheaper, and more accurate, all while enabling perfectly safe concurrent teamwork.
So as you start bringing multi-agent teams into your daily workflows, whether you are deploying code, auditing infrastructure, or parsing massive data sets, the secret to scaling their speed isn't just letting them all run wild at the same time and hoping for the best.
Right.
True multi-agent scale requires giving them the underlying structure to self-heal. It requires giving them the architecture to dynamically build tools to undo their own mistakes, and providing those advisory nudges so they can actively course correct when the digital world changes around them.
If we connect this to the bigger picture, this research opens up a wild new frontier for autonomous systems. Throughout this entire paper, these agents are dynamically creating their own undoable tools and resolving conflicts based on a fixed serial rank.
Right, that sigma priority number given to them by the system at launch.
Exactly. But as foundational LLMs become even more sophisticated at reasoning, what happens when we stop assigning their ranks from the outside? What happens when these multi-agent teams begin negotiating their own priorities and hierarchies in real time, literally arguing with each other to decide whose read-write operations are more critical to the mission's success?
Oh, wow. That is a fascinating thread to pull on. We started this deep dive looking for a clean, simple explanation of how agents avoid stepping on each other's toes, and we found an entire self-healing, time-traveling, tool-building ecosystem operating just beneath the surface of our terminal screens. I'm going to leave you with that to chew on. Thanks for joining us on this deep dive into CoAgent, and keep questioning how those AI tools in your stack are really operating when you aren't looking.